Hello students, I am once again Professor Sanjay Bhargav coming up with a new video on electric field, properties of electric field lines and so on. We pick up with the definition of electric field. Now what does electric field represent? The region of influence around a charge in which another charge on entering would experience a force. That means if you have a charge here and you have some region of influence here, then another charge when enters would experience a force. Then this region would be then called as electric field. We talk about two types of charges. One is called as source charge. A charge which can produce electric field would be called as source charge. Then what is test charge? The test charge is a charge which would be used to detect and measure the electric field that would be produced by the source charge. So electric field produced by source charge and electric field detected and measured by the test charge. Now in our second video we did a topic on superposition principle where we calculated the force that was experienced by the test charge Q0 due to system of source charges Q1, Q2, Qn, and that force was given by this equation. F would be equal to Q0 summation I is equal to 1 to n k qi upon ri ka square ri cap. This Q0 take it to the LHS. So what I get on LHS? F upon Q0 would be equal to summation k qi upon ri ka square ri cap. Now look at this equation very carefully. LHS, what does F represent? F represents force on the test charge. What does Q0 represent? Q0 represents magnitude of the test charge. So I can say LHS of the equation is a function of test charge alone, because F represents force on the test charge and Q0 represents magnitude of the test charge. Now come on the right hand side. K is a constant, electrostatic constant, and what is Qi? Qi represents magnitude of the source charge. And what does Ri represent? Ri represent their distances from the origin O. So RHS can be called as a function of magnitude of the source charge and their relative positions with respect to the source charge. LHS and RHS are mutually independent, because LHS is a pure function of test charge while RHS is a function of magnitude of the source charge and their relative positions. If they are mutually independent, then they can be put equal to the same constant. So let E be equal to F upon Q0 is equal to summation I is equal to 1 to n k qi upon ri ka square ri cap. Here E is known as the electric field. Now when I pick one part of the equation, E is equal to F upon Q0, then it can be rewritten as limit Q0 tending to 0 F upon Q0. That's the exact way of defining the electric field. So what is electric field? Let us say it is numerically equal to the force that would be experienced by a unit positive test charge which was placed at that point. So how do we say? We say E is equal to F upon Q0. Now if I can say Q0 is equal to 1 coulomb, then E would be equal to F. So electric field is numerically equal to the force that would be experienced by a unit positive test charge that was placed at that point. Now what would be the direction of electric field? The direction of the electric field would be same as the direction of the force experienced by the test charge. Now just see here, Suppose I have a source charge here Q, capital Q, and I place a test charge here. Since both are positive, Q0 would be repelled in the outer direction. Wherever you place the test charge, always it would be repelled in the outer direction. So this figure now represents electric field for the charge Q. So if Q is greater than 0, electric field lines are radially outwards. Similarly, if I keep a charge negative Q here, test charge is always positive. So this test charge would be attracted towards the charge minus Q. So the direction of the electric field is inwards. So these two figures, they just represent the electric field line for positive and the negative charges. What is the unit of electric field? Electric field, we said it would be equal to the ratio of force upon Q0. So force is measured in terms of Newton, charge measured in terms of Coulomb. So the unit is Newton per Coulomb. What are the dimensions? The dimensions of the force are m1 L1 T power minus 2. For the charge is ampere power 1 T power 1. This would be equal to m1 L1 T power minus 3 ampere power minus 1. So the dimensions of the electric field are m1 L1 T power minus 3 ampere power minus 1. What would be the electric field due to system of charges? That would be equal to summation I is equal to 1 to n k qi upon ri ka square ri cap. Where do we obtain this equation from? This equation is coming from this place. E would be equal to summation I is equal to 1 to n k qi upon ri ka square ri cap. So this gives me the strength of the electric field produced by a system of charges. Now we had put a limiting condition here, Q0 must be tending to 0. Why? The test charge must be as small as possible. As small as possible. Why? So that it does not disturb the distribution of the source charges and change the electric field produced by the source charge. Because electric field was equal to k q upon r square. If r changes, then definitely electric field would change. So what we require is the test charge must be so small that it does not exert an appreciable force on the source charge to change its position. If position changes, तो electric field change हो जाएगा. Now I like to calculate electric field due to a single isolated charge. Let us see, we have here a charge Q placed at the origin O. This would act like a source charge. Now what happens? We imagine we want to calculate electric field at the point P. Now to measure the electric field, what do we require? A test charge. So Q0 represents the test charge which is placed at a distance r from the origin O. Now how to calculate force on the test charge? Through Coulomb's law. So I can calculate force on the test charge is k q q0 upon r square and the direction is r cap. How do we calculate the direction of the force? Because Q0 would experience a repulsive force in the outward direction. So r cap is positive. Now what does the definition of electric field say? E must be equal to F upon Q0. So bring this Q0 this side. This would be equal to KQ upon R square R cap. The direction of the electric field would be same as the direction of the force on the test charge, that is radially outward. So the electric field would be equal to KQ upon R square. While for system of charges it was summation I is equal to 1 to n k qi upon ri ka square ri cap. Now electric field can also be defined graphically with the help of concept of electric field lines. Now how do we define electric field line? An electric field line is a curve drawn in such a way that the tangent at every point on the curve gives the direction of electric field at that point. Now suppose I have a curve like this, I can draw a tangent at this point then the direction of the tangent would give me the direction of the electric field at this point. Electric field line is a path along which a unit positive charge will move in space when placed in an electric field. So what is electric field line? It's a path along which a unit positive charge would move when placed in the electric field. इलेक्ट्रिक फील्ड में जिस डायरेक्शन में यूनिट पॉजिटिव चार्ज मूव करेगा उस पाथ को हम इलेक्ट्रिक फील्ड लाइन बोल देंगे. नाउ we have two type of charges here, a positive charge and a negative charge. So positive charge and a negative charge here. Now what happens if I place a test charge here? It would be repelled in the outward direction. So this would represent the field line. So all the field lines are radially outward for a positive charge, while for a negative charge they are all radially inwards. The strength of the electric field is same irrespective of the positive or negative charge, because magnitude, it's only the question of direction that is changing. So my first figure here would be representing electric field lines for a positive charge. Now for the positive charge, can we say like this? Electric field is spherically symmetric. And what does that word spherically symmetric mean? Same in all directions along the radius of the sphere. You imagine a charge Q placed at the center of the sphere. Then on the surface at every point the strength of the electric field would come out to be same. And that is why you call it as spherically symmetric. Electric field lines for a positive charge are radially outwards, away from the source charge, because they are always along the direction of the force that would be experienced by the test charge. Similarly for negative charge, field is spherically symmetric, same at every point on the surface of the sphere. Now electric field lines for a negative charge are radially inwards, and that is again along the direction of the force that would be experienced by the test charge. So always remember like this, for positive charge they are away from the charge, and for a negative charge the electric field lines are always towards the source charge. Now what are the important properties of electric field line? The first one, electric field lines, they start from the positive charge and end at the negative charge. You can just have a feel from this figure. Just imagine electric field line starting from the positive charge and finally moving and terminating at the negative charge. For single charges, they may start or terminate at infinity. Just see like this. Here for a positive charge they will terminate and move till infinity. For the negative charge they end at the source charge. The direction of the tangent at any point on the field line gives the direction of electric field at that point, already shown to you here. This represents the field line. The direction of the tangent at this point would give me the direction of electric field at this point. The two field lines, they never intersect each other. Why? Because at the point of intersection there would be two directions of the tangent, meaning there are two directions of electric field at a point, which is physically never possible. How can there be two directions of electric field at a single point? So we say electric field lines never intersect each other. Electric field lines are always perpendicular to the surface of conductor. If they are not, then there will be a component of electric field parallel to the surface of the conductor, which would cause a force on free electrons, causing their acceleration, which is against the laws of electrostatics. So what we are saying is electric field is always perpendicular to the surface of conductor. Suppose in this case the electric field is like this, then what will happen? It would have two components, one perpendicular and another is parallel. This is metal. And what does metal possess? mortal possesses free electrons. So they would experience a force F is equal to Q times E due to the parallel component. And what would the force do? It would cause their acceleration. An acceleration not permissible in electrostatics. So let us see. F is equal to Q times E. So on the free electron, it would be minus E times E parallel. Now force would be equal to mass times acceleration. So acceleration of the electron would be given by this equation E parallel upon M. If acceleration takes place, then it is against the laws of electrostatics, and that is why parallel component is never possible. Then which component is the leftover one? It is the E perpendicular, and that is why we said electric field lines are always perpendicular to the surface of a conductor. The number of field lines produced from a source charge is proportional to its magnitude. More is the magnitude of the charge, more would be the number of field lines produced. So how can we say number of field lines is directly proportional to magnitude of the charge? N is directly proportional to Q. So N1 upon N2 would be equal to Q1 upon Q2. Now, how do we come to know about the strength of the electric field? More is the number of field lines passing per unit area, more would be the strength of electric field. So how do we describe here? The relative density of field lines at different points indicates the relative strength of the electric field at those points. The number of field lines passing per unit area held perpendicular to the direction of electric field provides a measure of strength of the electric field at that point. So how do we decide? We decide by number of field lines passing per unit area. Like this area is small and it is containing 1, 2, 3, 4 and 5 lines. This area is large and it also contains 5. So what is number of field lines? 5 per unit area, the larger area. So strength of electric field is weaker here and strength of electric field is large here. Now sometimes we find out very closely knit field lines. So what we say is crowded field lines, they represent a stronger field, while the spaced apart lines, they represent a weaker field. So if the field lines are close to each other, it's a representation of a strong field, and if they are sparsely populated, then it represents a weaker field. Now what is neutral field? What is neutral point? The point at which the net electric field becomes zero is called as neutral point. So net electric field is supposed to be zero at a point, then that point would be called as neutral point. And no electric field lines, they are supposed to exist at the neutral point. So neutral point, the net electric field is zero. It does not mean कि electric field नहीं है. It just says the sum of the electric field at that point would come out to be zero. Now we would like to draw electric field lines for a system of two positive charges. These are the two charges here, Q and Q. We need to draw field lines. You just see, identical charges, they repel each other. So all the field lines are moving or having a curvature which shows that they are repelling each other. In this direction, you will find minimum number of field lines. This spreading of field lines in the perpendicular direction is called lateral expansion. And this lateral expansion, this is used to explain the repulsion between two identical charges. What is lateral expansion? It is nothing but a spreading of the field lines in the perpendicular direction. This is the axial direction and perpendicular to it is this one. So in perpendicular direction, the field lines are supposed to spread, and that is what is representing lateral expansion, explaining repulsion between two identical charges. Now we have electric field lines for a system of equal and opposite positive charge Q, and here is minus Q. Such a system is basically called as dipole, has two poles, a positive one and negative one. Here field lines would be moving from positive charge and would terminate at the negative charge. See, these field lines are also completing their path in space and seem to move from positive to negative charge. Near the axis of the system, maximum field lines are supposed to be crowded. So this is known as longitudinal contraction. The longitudinal contraction explains the attraction between unlike charges. And this longitudinal contraction means the crowding of field lines along the length of the system. So here all the field lines are supposed to crowd or come nearer with respect to axis of the system, and that is called as longitudinal contraction, which is responsible for explaining the attraction between two unlike charges. Now let us check what we have understood through this question. We have a question here. In the given figure, identify the polarity of the charge Q and Q dash. Also calculate the ratio of the charges Q dash upon Q. So we have a charge here Q dash, we have another charge Q. Now just see, from Q dash, 3 lines moving this way and 3 lines moving this way. On Q, these terminate, and the number of lines which terminate are only 3. So from here 6 and here 3. Now since the here field lines are moving away, so Q dash is supposed to be positive. So field lines originate from the charge. Q is supposed to be negative because field lines terminate at the charge. How do we find the ratio of the magnitudes? Q dash upon Q must be equal to N dash upon N, 6 upon 3, 2. So the charge Q dash is double the value of Q. So on the basis of our understanding, we can just compare the magnitude of the charges looking at the number of field lines in the figure. So today we were able to understand the concept of electric field, the properties of electric field lines, and how to draw field lines for different type of system of charges. So that's all for the day. Thank you very much. Just reminding you to subscribe the channel and press bell icon so that you can continuously receive the notification for our updates and new videos. Thank you.